Hello.
You are audible, sir. You are audible.
Yes.
Screen is also visible. Yes.
Okay.
We'll
Okay.
start, sir. We'll start.
Let's start. Okay.
Good morning to all participants. Welcome to the last day of our FDP program. And the session is on properties and uses of high performance concrete in construction by Dr. R.B. Kadirnaikar, sir, Professor B.C. Bagalkot, Professor and Dean B.C. Bagalkot. I'm honored to introduce today's resource person, who is also the guide for me, under whom I have completed my research at PhD. I welcome you, sir. Dr. R.B. Kadirnaikar, Professor and Dean BEC Bagalkot. Sir has completed his PhD from IIT New Delhi. Sir has completed ME in Building Science and Technology from IIT Roorkee. Completed civil engineering from BEB Hubli. Sir has total 34 years of experience. Sir has been involved in many many administrative work, such as he has been worked as a placement officer. He has worked as a member of BOE and BOS. He has worked as a head of the department for civil engineering, and presently he is working as a dean. Membership, sir, in professional bodies. Sir is a life member of ISTE, Fellow Institute of Engineers, Chartered Civil Engineer, member of Indian Building Congress, member of Indian Society of Structural Engineers, and member of Indian Concrete Institute. Sir has offered many consultancy services to many government and non-government organizations in areas of structural design of buildings, water tanks, shell structures, non-destructive testing, rehabilitation of structures, material testing, and concrete mix design. Sir has been awarded with gold medal for securing first rank in ME. He has received Best Technical Paper Award for the paper title Effective of Curing Conditions on Mechanical Properties. Sir has also received another Best Research Paper Award on modulus of elasticity of high performance concrete beams under flexural and experimental approach, conducted by COEP Pune, for which I am also the co-author. Sir, areas of specializations are high performance concrete, reactive powder concrete, geopolymer concrete, fiber reinforced concrete, concrete mechanics, design of reinforced concrete and steel structures, rehabilitation of structures. Sir has guided around 36 MTech thesis, and under Sir, 5 students have been awarded with PhD. I am one of them. There are 5 students who are working on 5 students are the research scholars working under Sir. Sir has published around 100 papers, 36 international journals, 8 national journals, 34 international conferences, 10 national conferences, and a few of them have communicated. Sir has completed many sponsored research projects, received 12 lakh for modernization of concrete laboratory, received 2 lakh for national seminar on IPRS, received 1 lakh for 2 days national workshop, received 2 lakh for SDP on maintenance of concrete highways, received 14.07 lakhs for project behavior of high performance concrete columns, received 12.7 lakhs for project durable concrete for sustainable development, received 10.25 lakhs for properties of reactive powder concrete. All these projects have been completed. Sir has been delivered many special lectures and guest lectures, including MIT Pune and IIT Delhi. With this, I am honored to welcome you, sir, for this FDP, and I thank you for accepting our invitation to be as a resource person for this FDP. Welcome, sir.
Thank you. Thank you, Mr. Momin, for your kind introduction and good words regarding me. I think I'm audible. Is the voice clear?
You are audible, sir.
Okay.
We have stopped the video because there hasn't been network issue. We will only operate with the PPT. Okay. Continue, sir.
Yes. The topic of my discussion today is properties and uses of high performance concrete in construction. So I have divided my lecture into three parts. One is we'll be starting with what exactly by high performance concrete, and then production of high performance concrete, and little about the selection of constituent materials and mixed design aspects. And after that, the properties of high performance concrete, and then uses, that is the application of high performance concrete. So this is the order in which I'll be delivering today's lecture. So let us start with the introduction to the high performance concrete. Of course, I'll not go back into the history of concrete and then utility of it. It is a popular material, widely used material, all those statements and these things you already know. So there is no need to go back to the history of conventional concrete. And of course, concrete is the most widely used material. Why it is used and why it is accepted widely, all those reasons, they are there. There is no need to dig into that. Yeah. But the fact is that concrete is a very essential material, and you cannot imagine any construction of a civil engineering structure without concrete. So it is widely used for almost all sorts of structures, right from water retaining structure to underground structure, to overhead tanks, to buildings, bridges, anywhere, any structure you need. And we are extensively using concrete for the construction of civil engineering structures. So, and you are also aware that there is a lot of advancement in the concrete technology, and with a growing number of tall structures, the use of this concrete is widening. And now we started with conventional concrete and switched over to high strength concrete, and then now we are using high performance concrete. So particularly for tall structures and special structures, the use of high performance concrete is becoming more popular. So, as you know, this HPC is an engineered concrete possessing the most desirable properties during the fresh as well as the hardened stages. So HPC is far superior compared to your conventional cement concrete or the conventional concrete that we call it as the ingredients of high performance concrete contribute most optimally and efficiently to the various properties. As you know that the constituent materials of your conventional concrete and high strength and high performance concrete being the same, then what makes difference in the performance is that in case of high performance concrete, we optimally use the constituent materials. In conventional concrete, the cement and some materials, they are not used to their full potential, and it is because of that we have some the performance deficiencies in the conventional concrete. So it is, you can say it is HPC is an engineered concrete, and it has the most desirable properties. Whatever for a particular or intended use, whatever property you desire, it is possible to tailor make the concrete to suit those requirements. So that is why the HPC is a concrete that exhibits the improved properties for a required performance as well as the long-term serviceability compared to your normal strength concrete as well as the high strength concrete. FLC is essential in many of the applications because of its higher strength and high durability or a better durability in order to reduce the sectional properties and enhance the mechanical properties, both in the fresh as well as the hardened state. In the 1930s, the first high strength concrete in Japan was developed. Yoshida developed high strength concrete with a 28 days compressive strength of 1 or 2 Newton per meter square by using a high pressure but without using a finer material. So earlier it was application of pressure that resulted into the high strength because they were not much aware of the microstructure. They were only bothered about the macrostructure, and then if high pressure is applied, then naturally the voids will come down and there will be increase in strength. That was the concept. So, but for an in situ construction, going in for these kind of techniques may not work So, but however, they were able to produce a high strength by applying high pressure. That was the earlier attempt, and later in 1984, the American Concrete Institute adopted high strength concrete as a concrete with a strength more than 40 or 41 MPa. And here, in my discussion, of course, there is no standard yardsticks for defining high strength and high performance as such. The strength limits that we are considering, they are time dependent as well as geographical location dependent. The concrete that was high in strength, for example, in 1960s may not be treated as a high strength now. So that is why it is time dependent as well as the geographical location dependent. So in 84, the America for the first time defined concrete with a strength more than 41 MPa as high strength. And they adopted these concretes in actual construction also. And further, with the production of super plasticizers in 1960s, and we were able to reduce the water cement ratio substantially. And the HSC was developed using super plasticizers in Japan. This method of reducing water cement ratio using a super plasticizer was widely used for the production of high strength concrete, since at the beginning, when they were the most of us were designing the concrete mix based on the strength, and they were able to get increased strength, and they called it as high strength. And at that point of time, they were not very much worried about the performance characteristics of the concrete they have produced. And they got the increase in strength, and they rightly called it as the high strength concrete. And then later on, there was a shift in attitude from strength towards the performance, and then they called it as the high performance concrete. So the design of high strength concrete is based on a strength criteria. As I said, the composition wise, there is no much difference in the conventional concrete or a normal strength concrete and high strength concrete and high performance concrete. And many times in the discussion in the literature, the high strength concrete and high performance concrete, the terms, they are interchangeably used. So the only basic difference is that your HPC has, with the strength, it has better performance characteristics also. The composition wise, of course, there's a very slight difference that when you compare with the conventional concrete, the differences are you have a lower water binder ratio in high performance concrete, and you'll have a large quantity of mineral admixtures or powder materials, and then the aggregates containing good particle packing characteristics, because these things make a basic difference. And high dosage of super plasticizer is a mess, because if you need to maintain the lower water binder ratio or lower water cement ratio or a lower water content, then this higher dosage of super plasticizer is essential. So this is composition wise. These are some differences. The moment we start talking about HPC, this basic difference we have to keep in mind, and then we have to go for the discussions. And of course, the microstructure level and microstructure level also, there are some differences. As we go on discussing, we'll be considering these points also in further discussion. Well, so when it was first designed, it was based on the strength criteria, and the results may also have incidentally, when I increase the strength, normally the water content is reduced, means it will have enhanced durability characteristics also. And with addition to this, then in addition to strength, we wanted to address the durability so that the resulting concrete will have the strength as well as the better durability, that is a performance. So, and in view of this, so when both the things were considered, HPC was developed. The Federal Highway Administration of America, it is known as FSWA, of the US Department of Transportation, in early 90s has sponsored several demonstration projects with the use of HPC. Since 1993, a number of bridges have been built using HPC across United States, Canada, Australia, and Japan, like that. And at that point of time, only 90s, 80s and 90s, they produced a concrete up to a strength of 96.52 MPa, and then have been successfully used these concretes in the actual construction. So before we proceed ahead, let us see how the high performance concrete is defined, and then regarding mixed design, and then after that we'll be going in for the properties. Let me make it very clear that there is no universally acceptable definition of high performance concrete so far. And of course, as I said, it changes from place to place. And of course, time domain is also important. But it is some of the definitions which are more or broad, embracing those. I have given some of them here. Of course, there is no a common definition for high performance concrete as such. As I said, that this high performance concrete, there is no universal acceptable single criteria for that. And then it depends on the required performance characteristics. So if you have offshore structures, then the performance characteristics is different. And then you have freeze-thaw resistance, then the requirement is different. So like that, what is the intended use and what is the required performance level? Based on that, many researchers and some bodies like ACA and all that, they have defined high performance concrete from different considerations. Then according to Mehta and PC Action, these two are very pioneers in the development of high performance concrete, contributed extensively for the mixed proportioning as well as the experimental testing of high performance concrete. According to Mehta and Edson, the concrete which possesses high workability, high strength, and high durability is termed as HPC. This is a most general. So here it is clear that it covers almost all the desired properties of the concrete in the fresh state as well as in the hardened state. So better workability is in the fresh state, and strength and durability in the hardened state. This was more broader this thing. And the second one, high performance concrete is something which demands much higher performance compared to a conventional concrete. So from a concrete compared to performance expected from your ordinary concrete, that is called as the conventional concrete. A concrete that meets special performance and uniformity requirements. If you these terms, if you slightly concentrate, as I said earlier, that the constituent materials of your conventional concrete and then the high performance concrete are the same, but what makes the difference is the microstructure of this high strength or high performance concrete. That brings about the change in the properties of the conventional concrete and the high performance concrete. The most common observations when it comes to high strength or high performance is that the material is more homogeneous on micro scale, that is millimeter scale or micrometer scale. So where is that is nothing but the uniformity, what we call. So because of that, and there is no pronounced transition zone between the sand and the paste, and then it has a low porosity, hardly 1 to 3%, and the proportionately lower percentage of capillary porosity, that is only 10% compared to 20 to 28% in case of conventional concrete. So these features make it distinct from your conventional concrete. So that is why it is concrete that meets special performance and uniformity requirements that cannot always be obtained using conventional ingredients, normal mixing procedure. And here, in case of HPC, mixing is also very important. There are a lot of research done only on the mixing. They have used different types of mixers and mixing time also, mixing procedure or methodology. That makes a huge difference. So so there has to be improvement in the mixing procedure also, and of course curing also, whatever the procedure that you follow for your conventional concrete. So you have to is not so. Let me close this. Am I audible? Hello?
Sir, you are audible, sir.
Audible. Okay. There was some problem here. Right. Yes. So mixing is also important, and another important this thing is curing practice. Also, you will come to know that here you need to start curing much earlier compared to your conventional concrete. Well, the another important definition was proposed by SHRP, that is the Strategic Highway Research Program. SHRP defines high performance concrete, mainly keeping in view the requirements of highway construction. So HPC for highway application on the strength, durability, and water binder ratio criteria as summarized below. The compressor strength is determined for the 100 mm diameter and 200 mm height cylinders. This concept earlier, we were strictly adhering to the bigger size, that is 15 centimeter diameter and 330 centimeter height cylinder. But it has been found later that even if you go for smaller sizes with maintaining H/D ratio 2, and you'll get reliable results. So that's why they used 100 mm diameter and 200 mm height cylindrical specimens. And water cement ratio is determined for all cementitious materials. And durability factors in terms of 300 cycles of raising and pie. So there was a thrust on strength as well as the water binder ratio, because you know that the performance characteristics, particularly the porosity, that is the diffusion characteristics or permeation characteristics, what we call, that depends on your water binder ratio. So they consider the strength requirement and also the water binder ratio and durability characteristics, that is 300 cycles of raising and pie. So in 6 hours, SHRP, it expects around 14 MPa just in 6 hours, and then 17.5 MPa in 4 hours, and around 35 Newton per square in 24 hours, and then around 70 MPa in 28 days. This is the high performance concrete. They accept this according to SHRP. And the water binder ratios varies anything between 0.35 to 0.4, and it depends. Even less than 0.25, 0.2 are also used. But the threshold limit is 0.35 nowadays. You go beyond 0.35, some of your performance characteristics, you may get strength, but some of the performance characteristics, they are impaired. So that's why nobody goes beyond 0.35. So 0.3, less than 0.3 or 0.35, like that. So, and after 300 cycles of freezing and pie, so 80% is the threshold limit. It should give at least 80% performance, and then only it is accepted. The most broader definition, widely acceptable definition, was proposed by the American Concrete Institute, ACI, has defined HPC as a concrete which meets special performance and uniformity requirements. Again, that is a inhomogeneity or a non-homogeneity, what we call it as. Okay, we are moving towards a non-homogeneous material to a more homogeneous material. So a concrete that meets a special performance and uniformity requirements that cannot always be achieved routinely by using only the conventional materials. So in addition to conventional, as I said, we are using the more finer materials and mineral admixtures as well as the super plasticizers. So not only conventional, so in addition to that, these two mandatory materials are also there. So we are going beyond the normal mixing. As I said, you can fix up the sequence of mixing and then placing also. So you have to go for refined placing techniques and then curing practices. So it almost covers everything. So this is most widely used or most widely accepted definition of high performance concrete. Well, so then summing up all these things, high performance concrete is a concrete having certain characteristics like easy placement, and compaction, because if there are some issues with the placement, then that will continue. Their compaction will also be problem. Then later on, that will affect the strength as well as the performance characteristics. So it should be easy to place. So easy placement is there. So if it can be easily placed, then compactability would also be better. And if these two things are better, then it will have an enhanced long-term mechanical properties. And it will also have high early strength. You have seen just in 8 hours around 17.5 MPa defined by the strategic highway, SHRP. Okay. So, and it would have high early strength and then high toughness characteristics. It will have more balanced stability, long life in severe environments. Such a characteristics cannot be obtained for a conventional concrete with normal procedures of mixing as well as the placing techniques. Well, so now let us see this is what the basics, that is some of the definitions. Of course, there are so many other definitions also. That is Civil Engineering Research Foundation, CRP, R.N. Swamy has also defined, Paul Gia. There are so many other researchers who have defined high performance concrete, but since we are more interested on properties and these things, so ACI is the most widely accepted. So let us not go into the much details of only the definition part of it. Well, so then how your high performance concrete is different from your conventional concrete. As you already seen that it has improved performance at the fresh state as well as hardened state. Then definitely then it would have a mechanical properties, improved mechanical properties, durability, and the behavior of HPC. It differs significantly to a very large extent as compared to a normal strength concrete and high strength concretes due to a dense microstructure by use of finer materials as well as the superplasticizers. So if anybody has studied the mechanical properties, why we have a particular type of behavior for conventional concrete, that is curvilinear stress strain characteristics, and then micro cracking, all those. So then you might have already studied or aware that those properties are basically because of the kind of cracking that takes place even before a conventional concrete is loaded. That is, a microstructure is responsible for the type of behavior that you have for your conventional concrete. So since you are changing a microstructure here, then accordingly there is a change in the behavior of your high performance concrete, because your HPC has a more dense microstructure, and definitely the cracking pattern here changes, and accordingly there will be a change in the mechanical properties of your high performance concrete. So then HPC has many advantages as compared to a conventional as well as your HSC. HPC can be advantageously used in construction of columns, beams, slabs, long span structures, any structure you name. You can use particularly where you have sub-zero temperatures or durability issues, then HPC can be effectively used. So the use of HPC has, of course, it will have improved mechanical properties. And once it has improved mechanical properties, then definitely there will be a reduction in sizes of the structural elements that you are getting. And once the dimensions are optimized, then definitely you'll have an increased available space, and also there will be a reduction in the overall dead load. And if there is a reduction in dead load, definitely there will be reduction on the total load that is coming on the foundation of the structure, and the overall economy would be there in the design of your concrete structures. This high performance concrete can especially be used effectively for structures exposed to the severe environments due to low permeability and high resistance to various environmental factors, wherever the performance issues are there. Okay. Then coming to the characteristics of how high HPC is identified, what are the bases? So in the definition, you already seen that it will have a high early strength, and very high early strength concretes also have been developed. So it is HES, high early strength, or high very early strength, like that. So it will have early strength, particularly for repair and all that. This is a very useful material. So high early strength and ultimate strength is also high. And then it will have a high modulus of elasticity, particularly in pre-stressed concrete, and then other issues where serviceability is a problem. So increased modulus is advantageous. And high abrasion resistance, like industrial structures, that is industrial buildings or industrial floors, and then pavements, that is a road pavement or airfield pavement. So abrasion resistance is another desirable property. And high durability and long life in the severe environments. Then low permeability and diffusion characteristics, because the permeability depends on the diffusion character, that is the permeation characteristics. Resistance to chemical attack, and high resistance to frost and de-icer scaling damages. In some of the countries where for a very long period of the year, there will be sub-zero temperatures. In that case, this frost resistance becomes a major issue. And toughness and impact resistance in bridges and all that are offshore structures. Then volume stability, reduced creep and shrinkage, ease of placement, then compaction without segregation. This is also a very important property, because a lot of voids will be there if it is not effectively compacted or if there is a segregation. So those were the characteristics of high performance concrete. And when we go for adopting high performance concrete, then there will be a reduction in the member size, as already highlighted, and that results in increase in the plinth area, usable area, and direct saving the concrete volume would also be there. And then reduction in the self-weight of the structure as the superimposed dead load with accompanying saving due to smaller foundations or reduced foundations. Then reduction in the formwork area also, because your structural sizes are reducing. Accordingly, the area of your formwork is also reduced, and cost with the accompanying reduction in soaring as well as stripping time and high early A's, gain in strength, high early strength or very early strength, what we call. The construction of high-rise buildings with the accompanying savings in real estate cost in a congested areas. We'll see in the application part, in the last part of this discussion, wherein it has been very effectively used for the construction of tall structures. There will be a reduced axial shortening of compression supporting members, particularly in tall structures and in heavy structures. The reduction in the number of supports in the supporting foundations due to the increase in spans. For suspension bridges or cable stayed bridges, you can go for the increased spans. Reduction in the thickness of floor slabs and supporting beam sections, which are a major component of weight and cost of the majority of the structures. Superior long-term service performance and the static as well as the dynamic as well as the fatigue loading. Particularly the bridge structures, higher resistance to freezing and thawing, chemical attack, offshore structures mainly, and significantly improved long-term durability and crack propagation. Reduced maintenance and repairs, if it performs better, if there are no durability issues, and then definitely the maintenance cost is substantially reduced. A smaller depreciation is a fixed cost, of course. If you are building new structures, then insurance issues, this issue, those issues, they're also solved. Well, you have attributed many good characteristics to the high performance concrete. Then if you use high performance, then you'll have so many advantages, this and so many things. Now let us see then how exactly to achieve this high performance, how to achieve high performance. That is basic issue. This high performance concrete is divided into 5 classes. And of course, it is, as I said again, not universally acceptable. Some based on the experience and the state of art, some classifications are done from time to time. So, and now this may be codified in the near future as Professor expressed. The comprehension of different phenomena involved in making high performance concrete. Right now, we do not have universally acceptable codified procedure for high performance concrete, particularly when we speak about the Indian context. we need to codify a lot of things. So HPC class 1 around up to 50 MPa, class 2 around up to 50 to 75 MPa, and class 3 100 MPa, and class 4 125, and class 5 150 MPa. Of course, some people have produced in the laboratory conditions more than 150 MPa also. But in our case, in our laboratory, we have produced up to 120 MPa. Worked on mechanical properties, 2 PhD theses we have produced up to 120 MPa. So now the question is how to achieve this high performance. You said it has this attribute, that attribute, and so many things. Good properties in the fresh state as well as in the hardened state. So to how to achieve this, that is the high performance, that is a basic issue. So the better durability performance has been achieved by using high strength and simultaneously lower water binder ratio or a lower water cement ratio. There are many techniques for this. The first technique is that we have to go for lower water binder ratio or a lower water cement ratio. So in general, if we speak generally, then better durability performance is achieved using the high strength and then lower water binder ratio or lower water cement ratio. And this approach is of design is based on strength and result. Of course, even though you are designing based on strength, but it instantly leads to a better durability also. So, then your high performance concrete will have the better performance, namely the durability characteristics. They are also addressed when you design it for strength. Though in the approach, the design is based on the strength and the result is better durability, it also results in that. And then it is the durability is addressed directly by optimizing the critical parameters, particularly the particle size required for the materials. That is, particle packing density technique is one of the techniques that we are using for producing high strength as well as the high performance characteristics. As I said, there are two basic techniques that are used for achieving high performance, two approaches basically. One is reducing the capillary pore. As I said, the microstructure level, how HPC or HS is different from or distinct from conventional concrete. I said that it has a reduced porosity. So then the reducing the capillary pore system such that no fluid movement can occur is the first approach for achieving high performance. So this is very difficult and to realize, and concrete will have some interconnected pores, but however, you can minimize. Totally you cannot avoid, but we can minimize. So then how exactly that is achieved in practice? So reduced capillary pores. We need to reduce the capillary pores. Then reduced water binder ratio. So when I reduce water binder ratio, at least the water whites will come down. And then reduced water binder ratio, then use of fine fillers like a silica fume. So wherein even the smallest of the whites will be filled. It also acts as a super filler as well as super pozzolana. And then there will be a good compaction. Then this is another technique that you go for a better compaction and the improved curing. So curing also is equally important. So this the first technique, that is reducing the capillary pores, is achieved by these four means. So reduced water binder ratio, use of filler metals like silica fume, fly ash, GGBS, ricer's cash, and another similar materials, and go for good compaction and improve. So if you take these precautions, then there will be an increased physical resistance. So the capillary pore system will be reduced, and automatically there will be an increased physical resistance. And if there's an increased physical resistance, automatically you'll be able to produce a durable concrete. That's a one technique that you reduce the capillary pore system. And the other technique is creating a chemically active binding sites which prevent the transport of aggressive ions, such as chlorides, is the second more effective method. And then this is the binding sites that you are providing. So how the binding sites are provided, that is use of SCMs, that is secondary cementitious materials. So it is a must, it is mandatory of course in HPC as well as in HSC. So we are using secondary cementitious materials, and this provides the additional binding sites wherein whatever your COH stress is released, and that will react with these things. It may be a blend of fly ash or other materials, rices, cash, metakaolin, fly ash, GGBS, or you can use these things individually, or you can go for binary as tertiary combinations of these things also. So then you will be providing additional binding sites wherein additional silica gel will be formed, and your concrete becomes more dense, and then you'll be able to achieve the high performance concrete. And of course, as you already know, the ideal high performance concrete will have a high performance, will have economy, it will have resistance to wear and deterioration, will also have resistance to weathering and all that. So these things are achieved by these two techniques. These changes when you make to mixes, then you will achieve these things. So when you control the permeation character, that is pore system, and naturally the permeation characteristics are also improved. The permeation is a major factor that causes premature deterioration of your concrete structures, and the provision of HPC must center on minimizing the permeation through proportioning methods and suitable construction procedures, that is curing, to ensure that the exposure conditions do not cause ingress of moisture and other agents responsible for deterioration. So the permeation can be divided into three distinct but connected stages of transportation of moisture, or vapor, or air, or gases, or dissolved ions. So the first, the property that is concrete takes in water by capillary suction. You also know that, and the rate at which the water enters, we call it as sorptivity, that is absorption test, or like that. There are many surface absorption tests and so many other things are there. So it is called sorptivity. So this is also one of the formation characteristics. The ease with which the fluid passes through concrete, and usually under a pressure differential, that the gradient is referred to as permeation. And then vapor or gas ions are sucked through the concrete under the action of ion concentrations, concentration differential. It is known as diffusion, particularly the chloride ions. Okay. So these three contribute sorptivity, and then this passage of liquids or fluids through, that is a permeation, and then this diffusion. All these three constitute what is called as the permeation characteristics. And if these three, if you control, if your pore system is controlled or pure or refined, then naturally your permeation characteristics they are improved. Means absorption is also reduced, flow is also reduced, and then diffusivity is also reduced. So in addition to these permeation characteristics, the requirement of the requirement of permeation characteristics, there can be other performance characteristics which may become the specific need for high performance concrete, and the other characteristics are the salient high performance requirements in addition to the permeation characteristics, or the compressive strength more than 70 MPa. It is already defined. In the very early strength, within 4 hours, 17.5 MPa for highway constructions particularly. Then early strength more than 35 MPa. Then high degree of impermeability, preventing ingress of water, moisture, carbon dioxide, sulfur oxides, air, oxygen, chloride. This depends on the permeability of concrete. High resistance to sulfate attack. This is chemical attack. Smooth fractured surfaces. Then absence of micro cracking. In your conventional concrete, you have a lot of micro cracking because of higher water cement ratio. So then the absence of micro cracking is there. Then high level of corrosion resistance. Since the diffusivity is low, then definitely it will have a high level of corrosion resistance. Then high electrical resistance. This is another measure, electrical resistance, another technique of measuring the durability or the diffusivity. Then high chemical resistivity, and high resistance to abrasion, erosion. These are the physical phenomena: abrasion, erosion, as well as cavitation. This concrete cavitation, particularly for hydraulic structures, spillways, and all that, you can effectively use this material because of reduced cavitation effect. Well, so all these were the characteristics of high performance concrete, and then now the question is how to achieve these characteristics. You said abrasion, this, that, diffusivity is reduced, and all those things. Okay. The parameters that are to be controlled for achieving those performance characteristics that we have just seen, you need to take these precautions. If you keep these points in mind, then you'll be able to achieve all those performance characteristics. So the parameters that are to be that need to be controlled for achieving the required performance criteria, the following parameters need to be controlled. So one is the water cement or the water binder ratio. As I said, less than 0.3 or 0.35. We prefer that. And then you need to control the strength. You have to concentrate on strength. Once if the strength is more, naturally the durability characteristics will also be improved. Then the densification of cement paste, densification, particularly the transition zone, where in conventional concrete you have a bigger transition zone and a lot of porosity in the transition zone. So densification of cement paste is being done. Then elimination of bleeding. So this is achieved. Anyway, we are going in for reduced water content. Water binder ratio means reduced water content indirectly. So the bleeding is eliminated to a larger extent, and the homogeneity of the mix. So here what is happening is we are going in for more powdery material, and we are moving from non-homogeneity towards the homogeneity. So homogeneity of the mix, we are in some cases we are also reducing the size of the aggregate. So routinely we go for 20 mm down size, but if you want higher and more than 100 MPa, then we go for less than 12 mm, so that is 10 mm or so, even sometimes less than that. So that brings a more homogeneity. So particle size distribution, as I said, the particle packing density is one of the techniques for producing the high strength or high performance or ultra high strength concretes like that. Dispersion of cement in the fresh mix. So this calculation problem is there. So now we are adding super plasticizer, so dispersion is better. Stronger transition zone, as I said, this is very critical. So your transition zone is improved, and low free line. So whatever free line is there, that is consumed by the mineral admixtures that we are adding, and there is no issue of low free line. It will definitely have a low free line compared to conventional concrete, and very little free water in a hardened concrete, because the water that we are using is very low. There is no question of any water remaining in your hardened concrete. So this is how, by controlling these parameters, you'll be able to produce high performance concrete with the improved durability characteristics. So then, as I said, then if you want to achieve those things, improved properties in the fresh state as well as in the hardened state, then mixed proportioning is also equally important. And we'll see how mixed proportioning is different. I'll not go into all the mixed proportioning techniques that are available, but because that will take the mixed proportioning itself is a big area, and it may need 1 or 2 lectures only for mixed proportioning. Only highlights I'll tell you. And equally important is the selection of constituent materials. Many times what happens is we go for choosing the materials the way we do it for conventional concrete, then that will not work. All the constituent materials that you are picking must be very judiciously picked up, and then you have to take a very stringent measures for selection of constituent materials. It may be cement, it may be fine aggregate, coarse aggregate, it may be water, mineral admixtures, or chemical admixtures. In all these cases, you have to be very cautious, and then they have to be selected. So you might be having a very good mixed proportion technique available, mixer available and everything, but if your constituent materials lack the basic requirements, then you will not be able to produce high performance concrete. So that is why the cement that you are choosing should be appropriately chosen. And for high performance concrete, as you are aware, we must have a lower C3A content, and increased fineness is better. And then it must be compatible with your high performance concrete, because compatibility issues will be there. And better you go for the fourth generation super plasticizers or HRWRs. It is C3A content that controls the rheological properties of your mix. So that is why we have to be cautious about C3A content. Around 5 C3A content is much better. Like this. So cement is equally important, and coarse aggregates, their size, their content, everything is important. Whatever properties that you have studied with reference to conventional concrete, they are still valid. Their surface texture, mineralogy, bond, mechanical properties, the compressive strength, everything that is important. But here you can go for what is called as a cubical shape or cubical size. That would be much better. It will have a reduced wide system. So reduced wides would be better. So your aggregate is important. The aggregate type is also important. Size is also important. As I said, as you move towards the increased strength range, then the size matters a lot. You cannot go for a bigger sizes. And your water binder ratio also depends on your size and texture. So that is why normally they go for 20 mm downside, but better thing is better suggested is 10 to 12 mm. And in some cases, you can also go to 20 to 25 mm, but in that case, the strength will be lower. So you have to properly understand the effect of each of these properties, and then only you have to choose the aggregate based on your strength requirements. Then mineral admixtures, you have a large number of varieties of mineral admixtures, like from fly ash to silica fume. They are available, but what are your performance characteristics or the intended properties? Based on that, you have to go for choosing fly ash or a silica fume or the SS gas, like that. So if you want more than 100 MPa, of course, you cannot depend on fly ash alone. You need to go for silica fume also. But if you are dealing with less than 80 MPa, there is no need to go for silica fume. With the fly ash alone or GGBS, you can manage up to 100 MPa. So like that, you need to think of what are your requirements, and accordingly, the mineral admixtures are to be chosen. You can go for, as I said, the combinations of these things also. Then the chemical admixtures are also equally important. They must have a longer chain length, durability issues, and all the compatibility issues mainly. You have to work out, and then the dosages and all that, what is chemical composition, what is what, all those things you have to have a clear idea, and then that is to be used. Otherwise, there will be a lot of issues. Slump loss problem will be there, and segregation problem is also there. Like that, so many issues are there. So the higher the solid content, better would be, or effectiveness will be better. Longer chain length, that is also better. Like that, those basic issues, they are there. So you have to study all those things, and then accordingly, you have to choose a proper super plasticizer, and you have to ensure that it produces a very dense concrete with a low permeability, and it minimizes the effect of heat of hydration, and then produce a concrete with a low air content. Sometimes there are some plasticizers which induce higher air content. That will be a problem. Then it should allow you to go for a lower water cement ratio. Like all these things, your requirement, keeping those things in mind, you go for large varieties are available. Naphthalene based are there, melamine based are there, lignosulfonate based are there, polycarboxylate based are there. You can go for combinations also. Of course, nowadays for very high strength is naphthalene, melamine, lignosulfonate. They are not very much used. You can go for fourth generation, mainly polycarboxylate ethers or carboxylic based. You can go for. So that's constant materials. We have to be very cautious in choosing the constant materials also. Well, so once you have selected appropriate material, then you have to proportion them. And let's see some few points on mix proportioning. So you need a special method of mix design here compared to your normal concrete, because we are dealing with a very low water binder ratio, and we are using chemical admixtures and different supplementary cementitious materials. And these would change the behavior of your mix in the fresh state as well as in the hardened state. So we have large number of methods already available. Of course, when it comes to Indian context, we have BIS method of mix design. And BIS method, of course, we cannot use for high strength and high performance. 10262 we generally use it, but it is cannot be directly used. Here, water cement ratio applicable for 40 MPa strength. So is higher than 0.3 or 0.35. So that is why it cannot be directly applied for high performance concrete. So in the earlier 80s, there were no standard mixed portions available for HPC or HS, you can say. And during that time, Neville has presented some typical mixes. Based on that, he proposed some guidelines. And people were using those guidelines and by and large going in for a trial method. You can say going in for one combination and then observing the behavior and then making some corrections to that. And like this, by and large, it was a trial and error, you can say. And they used to go list all the mixes available in the literature and then use their own techniques and produce high strength concrete like that. So this list A to D, there are 9 mixes he selected, and A to D are from United States, and B to I from Canada, and then G from Morocco, and H from France. He listed and then he gave some guidelines, and based on that, many people produced the high strength concrete. And now, of course, some mixed design methods available for us based on various published literature, like very popular one is Mehta and Edson. The ACI method is also there. ACI is basically for high strength concrete, and that you can extend 363 that we have code. So you can extend it for high performance concrete also. And Edson has refined his own method that takes into account the rheological properties of the mixed design also. And then a modified mixed design procedure is also there. LCPC method is also there. And this modified mixed design procedure utilizes optimum water content, the efficiency factor of mineral admixtures. There are also guidelines for the use of high performance concrete in various projects concerned with transportation, BS 18 British standard. And, there are so many techniques. So the mix that I was talking about, A to F, A to B some countries, and then C to I, one more countries, and F like that. So comparison like this would help you to take some decisions based on your requirements. So then, of course, earlier the cement content was higher. Say they were going in for 530, 500, more than 500. Normally, some people also used around 600 also. But keeping in view the heat of hydration, and it is not advisable nowadays, because then the super processors were not that effective at that point of time. So that's why they were resorting to a high cement content. But now you can go for reduced cement content. Some people are using around 300 to 350 and still producing 100 MPa with the increased fly ash content or silica fume content. So this would only give you, so you'll find that the main characteristics that the water cement ratio or water binder ratio. This is the main, we have seen the two techniques that reducing the water binder ratio. So 0.22, 0.27. So like that. So they have reduced the water binder ratio, and by virtue of that, they were able to get a high strength. So coming to our BIS method, that is 10262 2009. 19 has also come now, of course. The code, the earlier code, of course, was listing up to M60, and it has standard deviation values also. And as the strength increases, the standard deviation value also they have increased. But when go for a very high strength concrete, this unduly high standard deviation value may lead to a lot of reserve strength and some uneconomical mixed proportioning also. So that is why that is there in our case. But in some of the ports, what they do is instead of standard deviation, they go for reduction in the strength, and then some factor they divide it by some factor, and then increase the strength and then design it for that. So, but in our case, the standard deviation values are increasing as the strength is increasing. But really speaking, what happens is if I go for more and more strength or increased strength, normally I go for, you know that the standard deviations are basically dependent on the variability in the properties of the mix you are targeting. So since as the strength increases, you are going in for more and more stringent method of selection of materials, mixing, proportioning, and then placing. Naturally, you have a better quality control and the standard deviation has to come down. But the technique normally we are following is we are increasing the standard deviation values, so that we need to think also, of course. And the graphs that are given in the BIS code, the general relationship between water cement ratios for M20 for 20 days strength for 52 MPa. So this and then the other these things for a 58 MPa. These were much higher than the limits that are normally fixed for the high performance concrete. The high performance concrete now, of course, in the 2019 code, they have listed up to 80 MPa, also 70, 80 MPa, and with the water cement ratio of 0.25. Then those things yeah, you can accept. But in the earlier version of the code, so you have a compressor strength MPa, and now, we have to produce, if I want to produce more than that, then there were no data available. And as per the finding out water content, we have the tables available there. And the water cement ratio in that table was 0.35. Then the water corresponding to water that we are getting using these tables is around 200 to 180 kg per kilometer. And this is much higher than what the people have used in the research. So we need to go for less than 150 or 140, around 145 or less than that. So that is why, so then if you go for such a high content of water, normally the pore system will not be refined. So, and the water cement ratio should be less than 0.3 or less. And even if I go for a water cement ratio of 0.3, and the cement content that I'm getting for this is around, with this water content, that is 200 to 180, it will be around 667 to around 600 kg, which is much higher. So if you get less than 500 or around 450, that would be a better cement content. Yeah. So the BIS method, even it allows zone 4 sand, and then to go for zone 4, and then you'll have this less than 300 micron, around 50%. And but HPCs usually very low water content, and this large content of small particles, less than 10 microns of sand, would reduce the workability of HPCs. And normally we do not prefer much of finer material because we are going in for a more binder content, and we already have more finer materials in the form of binder material, or you have mineral admixtures available. That's why it's not advisable to go for say less than 300 or like that, or 600 like that. So that is, these are some of the drawbacks of existing BIS method. ACI method, of course, slightly better than ours, up to at least up to 60 MP. And then here also the water band ratio, the minimum water content ratio is 0.3. Sometimes we need to go below 0.3, then it becomes a problem. Road note number 4, here also the water cement ratio is minimum is 0.35, but we normally go below 0.3. So then you can apply, you cannot apply this. IRC, this was very popular technique. And here the minimum water cement ratio is 0.4, and then the strength is around 50 MPa. So since we are dealing with less than 0.3, less than 0.3, so then we cannot adopt this technique also. So then the most common techniques that are followed are the one proposed by PC Edson, and based on his experimental work, and he has some mathematical calculations also that he has proposed. So this is these are the graphs proposed by PC Edson. You have see water band ratios, and then this thing, you have a band here. This band is given. It depends on the material properties that you have selected. Based on that, for the same water cement ratio, for the same strength, you can vary water cement ratios. So the water band ratio is determined from this figure for a given 28 day strength. measured on cylinder, of course. This is measured on cylinder. So the why this band, owing to variations in the strength efficiency of different supplementary cementitious materials. The curve in figure shows a broad range of water binder ratios. And based on your requirement and efficiency of the material, different supplementary cementitious materials you are using, you can choose the water cement ratio. This is this can be used only as initial point or starting point. But your experience matters a lot in this case. So these are different test standards. Of course, these are available. You can find them. Okay. So what is the step? So you from the first graph you choose water binder ratio, and then once you choose water binder ratio or water cement ratio, then we have to find out how much is water content. The amount of water required to be used is determined by a simplified approach based on the concept of saturation point. So they have proposed one graph here, and based on that you can decide how much initial water is to be added. So saturation 0.6, then 120 to 125, and up to 1.4, 155 to 165 liters per cubic meter. It is only a beginning point, as I said. So the saturation point is point at which any increase in this you already know. Using a simple Marshall test, you can conduct, and then you can find out what is the saturation point. And if the saturation point of supervisor is not known, then it is suggested to start with say around 145 liters per cubic meter. You can start with. As I said, lot matters on your experience actually. And to design a mix, it is not that you have to start with 120 or 125 like this only. You can add around 5 liters per cubic meter of water for these values, and then you can start with your first trial, and then based on the experience of that, you can go on modifying these things. Okay. So now based on saturation point, then we are choosing the water content. And once you know the water binder ratio and water content, then you can find out the binder content, and you can get, and then once you decide the binder content, and out of that, what should be your SCM, secondary cementitious material, how much percentage you want to replace, and accordingly that is to be decided. And once you choose the binder content, then you need to go for a coarse aggregate content. It depends, as I said, on the characteristics of your basic also, particle shape, size, and so many things. If the shape of CA not unknown, or you are not very sure, if there is a doubt about all those things, the properties, you can start with around 1000 kg per cubic meter of coarse aggregate content. If you have a clear-cut idea regarding what type of these things and everything, so then you can start with so there is ranging from 950 to 1150, elongated and flaky. So in this range, an average in this range, then cubic shape you can slightly go for increased, and then rounded still more. So like that. So based on the type of aggregate, you decide between 950 to 1150 kg per cubic meter. And after that, the air content, and the authors normally suggest around 1.5%. But of course, it also depends on superclasses that you are using. Or if you want to find out what is the actual air content for combination, and based on that you can take. So normally it is around 1.5. That much is considered the mixed proportion. And superprocessor dosage, by Marshall test you decide. And if you don't have any idea, then you start with 1% dosage, and then go on adding based on your requirements or based on performance in the test state. You can go on changing that. Then final mixed proportions determined by the absolute value method. Of course, all the techniques use the absolute value method only. So using absolute, so other constant materials, whatever they are there, you can use that. And if you want to still refine it, sometimes the people also go for, particularly when it comes to the superprocessor, they separate like liquid content in that, and then the liquid content as well as the solid content. That level of refinement you need. You first find out the total volume and divide that into a solid as well as a liquid component, and then accordingly you can do the corrections. So this is how using PC action method. As far as my experience is concerned, action method gives a better results compared to the all other techniques that are available in the literature. So once you design, and then you have to start with the producing it, and then in the fresh state, what matters, the properties of a fresh concrete. So as you have seen, it is HPC is characterized by special performance both short term as well as a long term. So it should give you a better properties. So the one of them being the workability of high performance concrete, and normally it should have HPC must have exceptionally good workability because we are using admixtures like superplasticizers, that is SRWRs we are using, and we are also using higher level of cementitious materials like fly ash, silica, fume, GGBS. These things are also added, and it will definitely have a better workability compared to conventional concrete. And HRWs, it's used to overcome the reduced workability due to the reduced water content, and it also reduces the stickiness, that is a flocculation. Deflocculation will be there. And then HPC normally good workability, even at a low slump also, it is more workable compared to conventional concrete. And pumping characteristics of high performance concrete, they are very good. It was in one of the examples I'll give later on. It was pumped successfully to a 79th story of South Walker Tower in Chicago in 1993. Paul Zia did mixed design and for this. So even up to 79 stories, they were able to pump it, not place it. So placed by pumping. So it means excellent workability characteristics. So this is the South Walker Tower in Chicago. It is a 79-story tall building, and up to the top floor or the story, they were able to pump the concrete. So pumpable concrete, as you know, should have very high slump, uniformity. Yeah. So concrete rheology is another important property, how it behaves. So stiffening, hardening, all those things. This is governed by physical as well as the chemical factors. And among the physical factors, the grain size distribution, the binder particles and aggregates, and then shape of the aggregates also matters. The beneficial effect of adding silica fume powder in a high performance concrete mixture improves the grain size distribution. That is the particle size distribution, what we normally call. So when a minute spherical silica fume particles are well dispersed in the cement water system, they can disperse water molecules from vicinity of the cement grains so that entrapped water molecules between the flocculated cement particles can be freed and thus contribute to the fluidizing of the mixture. The flat and elongated aggregate particles are detrimental. Of course, we are not using them. As I said, the cubical shape is better rather than elongated or a flaky, and are detrimental to workability and even for strength also, and even from this transition point of view also, transition zone point of view also, they are not good. So we have to go for cubical or spherical shaped aggregate, and they produce a better workability. So among the chemical factors affecting the rheology of concrete are the initial reactivity of the cement and supplementary cementitious materials when they come in contact with water, and the duration of the so-called dormant period. So this is also important. Then coming to the setting or stiffening of the high performance concrete, the setting time of HPC vary depending upon the value of the different cementitious materials you are used, and also on the dosage of superplasticizer. Some of these superplasticizers, as you have seen, also act as retarders. So, so they causing a delay in the setting time. So before you use any particular brand, you have to be very sure that what extent of retardation it causes. This may cause slump loss also and reduces very early strength of HPC, even though the strength at 24 hours may be relatively high. Retardation longer than 24 hours has been experienced in the field without harming the ultimate compressive strength. Of course, the initial setting you did, if you go for higher percentage, particularly more than 2%, then 2%, 3%, 4% like that. In some cases, there will be a retardant, means the setting is delayed. Even after 24 hours, it will not set 40, sometimes 48 hours, 50 hours, 60 hours. Some case in our own laboratory, one particular brand of superprocessor, we are not able to get the setting even after 72 hours. So all these things, they must be absorbed. An extensive set retardation can take place when the superprocessor dosage used is a quite high, or even a set retarding agent is used, particularly for RMCs, or if want to pump or want to transport it for a longer distance. We are going in for set retarding agents also. In that case, you have to be careful. You have to work on, properly understand its effectiveness or behavior, and then it is to be used. Severe segregation is observed from time to time when an error in the dosage of superprocessor or in the amount of mixing water occurs. We have to be very precise while adding the constituent materials. To overcome the problem of reduction in a high early strength, melamine superprocessor may be used instead of naphthalene. Of course, this is literature related to earlier period. Now, of course, most of us, we are neither using naphthalene nor melamine. We are going in for the fourth generation. So there is, but of course, if you have a choice between SNF and SMF, in that case, this will help you. Well, so that is how the properties about the prostate. Slump loss problem, of course, a main this thing that you have to slightly take care of. Then otherwise it will have better workability. So then after that, curing is also important. It's more important compared to normal concrete because of lower water bond ratio. Loss of water may interrupt the hydration process, and low bleeding may cause shrinkage cracks also. That's why in some cases we resort to earlier curing of high performance concrete. If water curing is applied as soon as HPC concrete temperature begins to rise, most of the heterogeneous shrinkage can be eliminated. Depending upon size and the type of the structural element, different solutions for curing may be employed with a minimum of 7 days of curing to minimize shrinkage. To minimize the shrinkage, but in no conditions the period of curing shall be less than 3 days, because they go over combination. It doesn't mean that only 7 and 3 days. Say you want to apply curing compound in the first initial period, normally they go for moist curing, and then after that they resort to other curings. But there should be a sufficient curing that should be done. The most commonly used curing method to cure a shrink-off-in concrete, namely with a wet burlap. Initial rapid loss of moisture will be there when you go for using the silica film particularly. So you can use wet burlap or a plastic sheeting, and then curing compounds recommended with a wet curing. So HPC, which contains GGBS under non-standard curing conditions, was found that due to lack of moist curing, the compressive strength of concrete reduced up to 50%. So the another important property of your HPC is a stress strain behavior. Stress strain. Some of these stress strain occurs for different grades of concrete. This is a conventional concrete when strength increases, increased, and increased. So you'll find that there is a distinct difference in the shape of the stress strain curves for different grades of concrete. There's a change in the ascending part also, and the ascending part of each of these curves is also not similar to the others, and peak behavior as well as the post-peak behavior. So they are distinctly different when the strength changes. Since this behavior is basically because of as the high performance concrete exhibits a less internal microcracking compared to the conventional concrete. So this distinct behavior is observed. So you'll find that in case of very low grade concretes, you have a totally curvilinear behavior. And the ultimate stress and the peak strain, they are different. As the strength is increasing, this linear portion, find that now the linear portion is increased to this, the linear portion is increased, the linear portion like that, the linear portion is increased. So the ascending part is different, and the stress level to which this linear portion reaches is also higher as the strength increases. In your conventional concrete, normally it is around 20 to 30%, and then for a very high strength concrete, it goes even up to 60% of its ultimate strength. Right. So that is a distinct behavior. Ascending part and the peak part also, you'll find that you have very extended platea at the peak here, but this is reducing as the strength is increasing. The descending part also, you'll find that there is a difference in the post-peak behavior also. This is called what is called as a snapback behavior. So wherein you have very extended stress strain curve for lower grades, and as you increase so the post-peak behavior, there is a difference. So the slope of the descending part becomes steeper for HPC. So you'll find that this is more steeper compared to this, So to obtain a descending part of the stress strain curve, it's generally necessary to avoid the specimen testing system interaction, what we call it as a Platon effect. So, and also you should go for closed loop systems rather than stress control. You have to go for a strain control, then you'll be able to capture this behavior particularly. So HPC exhibits, so this increase in the linear stress level, and then you'll also find very interesting observation is that the peak strain here is 0.002, and now for this grade, say around 600, the strain is increased, and for this the strain is increased, and for this, so again the strain corresponding to the peak stress, there is an increase. So some people have observed even up to 0.003 of strain compared to the 0.002 what normally observed in case of conventional concrete. So here there is an increase in the peak strain and the peak stress. Of course, the descending part of the stress strain curve. As a result, the relative increase in the lateral strain is less for high performance concrete. Less micro cracking means naturally the lateral expansion is also less. The lower relative lateral expansion during the inelastic range may mean that the effects of triaxial stresses will be proportionately different for HPC compared to your conventional concrete, and the influence of hoof reinforcement is observed to be different for the high performance concrete. And many people, of course, have proposed the empirical equations for the stress and characteristics of high performance concrete. And of course, there is no single this thing and 100% accurate this thing. Equation that takes care of ascending part, descending part, and the peak, all those things. Some of them, their equation fits well the ascending part, but fails miserably in the descending part. And up to peak, it is okay. And like that, there are so many equations. And those who are interested in the post-peak state of a stress strain curve, for use of concrete researchers have proposed a number of mathematical equations that you always see. And this is the one proposed by Thorenfeld and Tomazovic and Jensen earlier. And later on, of course, Collins, Mitchell and Collins and McGregor have suggested so many equations. And in the post-peak, we need to do some corrections. These are the equations. If you give, so go on giving different strain values, and then you can generate a stress strain curve. So the second property of hardened concrete is compressive strength. As you know, the strength is more in this case, as the microstructural differences between the hydrated cement paste and the transition zone and the bulk cement paste play an important role determining the strength characteristics of concrete. This is very developed Weibull weakest link theory. You have studied earlier that the transition zone is a weakest link. So now it has been strengthened, and by virtue of that, you have the increased strength. So in a usual concrete, the transition zone is typically 0.05 to 0.1 mm wide. Now it reduces in this case, and it has relatively large pores and large crystals of hydration products, that are CH crystals. So porosity is also higher, but now it reduces in this case. Therefore, according to this theory, when the concrete is subjected to a given stress, the cracks first begin to develop in the transition zone, but now the transition zone is strengthened. The compressive strength of HPC is higher than the normal concrete, for more than minimum is 60 MPa. This property is influenced by various factors like material properties, proportions, water band ratio, degree of hydration, rate of loading, method of testing, all those things. Water band ratio effect also you see. So based on the water band ratio, they are also classified. The increase of compressive strength increases with the silica film content up to 20%. Of course, the optimum is 10 to 15%. Very few people have gone beyond 20 because you'll have beyond 20%. There is no pronounced effect on the strength. So that's why normally in the range of 10 to 15% we use it. The increase in strength of concrete depends much more on decrease in the water cement or water binder ratio. Also the replacement of mineral admixtures. Metakaolin is a good pozzolanic material with a partial replacement, 15 to 20%. And in this range, with a water binder ratio of 0.4 to 0.35, they are able to get 50 to 75 MPa strength, and 0.35 to 0.3, it was 75 to 100. Then 100 to 125, 0.3 to 0.25, and less than, say, in the range of 0.25 to 0.2. So it's around 125 MPa. The early strength largely depends on the dosage of superpressure and the water band ratio. The various composition of HPC may significantly reduce the early strength of HPC, and it is necessary to control the composition of HPC so as to get the required early strength to suit the particular field conditions and control the early strength of your HPC. And another important property is the tensile strength. Hello, am I audible? Hello, hello.
Yes, sir, you are audible. You are audible.
Okay, no problem, no?
No problem, sir.
Yes, yes. Okay, I'll continue. Tensile strength, the one of the major advantages of high performance concrete is high tensile strength. Of course, there's a no pro rata increase compared to compressive strength. But compared to normal concrete, it has a higher tensile strength, and you know that the cracks propagate very easily if the tensile stresses exceed the tensile strength of the concrete member, and that may affect its durability also. The new generation of high performance concrete overcomes this problem due to its high tensile strength. The addition of cementitious materials or SCMs like silica fume or fly ash, they densify the concrete microstructure and enhances the tensile strength of the concrete. The optimum percentage of silica fume, as you have seen earlier, is around 15%, 15 to 20, 15, even though they define, but 15 is the best. Usually the tensile strength is measured from the empirical relationships with the compressive strength. All other strengths, tensile, shear, all those things we express in terms of the compressive strength. The same you can extend it for high performance concrete also. And many researchers have developed empirical equations for finding out the tensile strength in terms of the compressive strength. And some of them I have listed here. And whatever expressions that you have for your conventional concrete cannot be directly applied and cannot be extrapolated for high performance concrete. Sometimes they give wrong values or not reliable values. So this Sen Gupta split tensile strength 0.248 into FC raised to 0.717. FSP is the split tensile strength here, and FC dash, FC prime is a 28 days compressor strength. So almost all same look again in 2005, and then CBFIP in 78.273 FC raised to 2/3, and Keras-Miller-Nielsen this is 0.54. This was basically done for high strength concrete long back in 81, and it worked well up to 80 MPa, but beyond that it doesn't work better. And then the other ACI committee proposes 0.59 to FC dash raised to 0.55, and it is applicable to 21 to 83 MPa, they say. And Ahmad and Shah in 85 proposed 0.462, and then up to 84 MPa you can apply this. Like this, many expressions are there, and whichever suits your requirements, accordingly you can use. And then another important property is the modulus of elasticity of concrete, and everyone generally agree that the elastic modulus of concrete increases with its compressive strength, and the modulus is greatly affected by the properties of the coarse aggregate, amount of coarse aggregate, all those things. It depends on the paste intent and everything. The Young's modulus of HPC is an important short-term property. This is useful for design point of view also. It is generally related to the compressive strength, as you already seen. As the strength increases, it increases. It depends on the parameters like aggregate type, mixed proportions, curing conditions, rate of loading also. And then the larger the amount of coarse aggregate, it will be different. And higher would be the modulus of elasticity on these scales. And the specimens tested in a wet condition indicated around 15% higher elastic modulus compared to the dry conditions. That was basically because of the drying case that takes place in COVID. And many researchers have proposed empirical equations for finding out the modulus of elasticity. And EC is equal to say 3.32 root FC dash plus constant 6.9. Keras-Miller-Nielsen and Slate, and the Winter also, of course. And then this is CBFIP recommendation. And this is OX, and this is CBFIP again, Norwegian core, like this. So really, there is no universally acceptable, a single this thing equation that can be applied for the whole range of strengths that you are producing. And some of them are applicable only up to a particular strength. Then some of them are applicable to beyond some range of strengths like that. So then based on your requirement, you have to use the appropriate this thing equation that is available. Then the another mechanical property is the Poisson's ratio. Experimental data values on Poisson's ratio for FPC are very limited, because since the experiments to be conducted are very typical and difficult, most of them have worked only on the compressor strength, behavior, stress and characteristics. But Poisson's ratio work is a bit difficult. So very limited this thing is available on Poisson's ratio. It's a Pernichon and Klegger reported a Poisson's ratio for a compressor strength ranging from 55 to 80 MPa between 0.2 and 0.28. And they concluded that the Poisson's ratio tends to decrease with increasing water cement ratio, maybe because of increased water cement ratio means that is a more micro cracking, more pores and more micro cracking. And Kaplan found values of Poisson's ratios for determined from dynamic measurements lie between 0.23 and 0.32, and regardless of the compressor strength, force aggregate, and he has tested the concrete from 17 to 79 MPa. So based on the available information, the Poisson's ratio of high performance concrete in the elastic range seems to be comparable to the expected range of values for lower strength concrete. No much variation has been observed. This is the experiment conducted in our laboratory for high performance concrete. Then the modulus of rupture for a usual concrete, the modulus of rupture and the splitting tensile strength are quite low and do not vary much, because they are very much influenced by the tensile strength of hydrated cement paste. For high performance concrete, the water binder ratio is low and paste content is higher here, and the compressor strength vary on a wide range. So the relationships that have been suggested for a compressor strength and the modulus of rupture. For a usual concrete, lose some of their predictive value when going from usual concrete to HPC due to a change in the composition of the mix, you can say. Splitting tensile strength, they were studied the relationship between the indirect tensile strength and the compressive strength of concretes in the compressive strength range of 83 at 28 days. And at a low strength, the indirect tensile strength was observed to be around 10%. And but when it comes to high strength concrete, it was observed to be around 5 to 8%. The tensile splitting strength was about 8% higher for crust rock aggregates concrete than for a gravel aggregate. Also, the indirect tensile strength was about 70% of the flexure strength at 28 days. Momin, hello. Hello.
Hello, sir.
Hello. How long I can continue? Is it okay? What is the time that?
Actually, it was till 12:30. Sir, you can continue, sir. No issues.
So I have a few more properties, 3 properties, and then some applications. So I'll rush through these remaining slides. Is it okay?
Okay, sir. Okay.
Another 15 minutes or so.
It's okay, sir. It's okay. Continue.
Coming to the shrinkage, normally the perception is that since we are going in for a more cement content or binder content, and high performance concrete will have higher shrinkage. But that's not true. Concrete shrinkage is both it's a phenomena. The decrease with the apparent volume of the concrete and a quite complex phenomena. And the shrinkage, when it comes to shrinkage, and then ATAL Navale had a detailed study. So we have plastic shrinkage and develops at the surface of the fresh concrete when it is subjected to a surface drying. And your autogenous shrinkage basically depends on the self-desiccation chemical phenomena. Then drying shrinkage due to the loss of water in hardened concrete. And here it is less because we have less internal water in case of high performance concrete. So the thermal shrinkage which follows a decrease in the temperature of concrete, and carbonation shrinkage. This is there. It depends on the permeability of cover concrete as well as the thickness of a cover concrete. So since your cover concrete here is very dense, so this is also reduced. So all these things contribute to the total shrinkage. And the premature cracking of concrete at early ages is due to the shrinkage. And this in turn affects the performance as well as the durability. So HPC, of course, total shrinkage is less, but plastic shrinkage, it is vulnerable because you have a lower water cement ratio. The rate of loss of moisture from the surface, if it is much higher compared to the rate of bleeding being less. So normally there will be, it is more vulnerable for shrinkage. The lower drying shrinkage in HPC is due to water binder ratio. The shrinkage reducing admixtures also you can use. And they reduce the surface tension. And the shrinkage reducing admixtures is capable of reducing drying shrinkage. That's a major concern, around 30 to 40%. And 30 to 80% reducing the premature cracking by the HPC. So these shrinkage reducing admixtures, they are water soluble and developed in Japan. So it's added by 1 to 2%. Drying shrinkage can also be reduced by use of ultra-fine GG-based particles, silica fumes. Then the other binders, you can reduce that. Then coming to the creep. Creep is one of the important long-term properties used in the design and analysis of structures. As you know, it depends on the plasticity and flow properties of the concrete. And creep is important in accessing the long-term deformation as well as the performance characteristics. Creep and shrinkage are both interrelated. The property of creep of HPC is remarkably different from that of normal concrete because of low permeability of HPC compared to normal concrete. The value of creep coefficient decreases with increase in the strength or decrease the water binder ratio. And here we have a decreased water binder ratio and hence creep will be less. The value of creep coefficient is lesser in HPC as compared to the normal concrete. Use of this shrinkage reducing admixtures also reduces the creep. It reduces shrinkage also, but in different capacities. And coming to ductility, as the general notion is that as the strength increases, it becomes brittle. That is true also. The compression tests show that the stronger the concrete, the more brittle it is. And this could be of concern since modern design methods take into account the plasticity of materials. The flexure test run on the reinforced HPC beam so that the ductility is similar to that of beams with ordinary concrete. So the material alone may be bit brittle, but when you do the design and do a proper detailing, then whatever level of ductility you want to imbibe in your structure, that is possible. Care should be nevertheless be exercised concerning HPC elements such as columns and submitted to axial loads. Experiments are being carried out in France in order to set the rules for concerning minimum longitudinal steel and transverse reinforcement in such cases. Coming to the fatigue strength, since it is brittle, its ultimate strain capacity doesn't increase proportionately with increase in strength. There is an increase, but it is not proportionate. And then FPC, the elastic modulus of the paste and that of aggregate are more similar, thereby reducing the stress concentrations at aggregate paste interface, and it is susceptible to fatigue. So thus, due to reduced micro cracking in HPC, the fatigue life built up damages are smaller when compared with those in normal strength. Coming to the applications, not take much of your time. So you can use for highways, bridges, multi-story buildings, high strength and superior durability characteristics of performance of concrete. It is used in bridges. The examples: Joigny Bridge in France, Great Belt in Denmark, Akekawa in Japan, and Willows Bridge in Canada. High-rise buildings, Water Tower Plaza, US, Navascote in Canada, and tunnel applications, La Boma in Village, France, and Marseille in UK, and Pements in Norway, highways in Paris Airport applications. In Joigny Bridge, these are fixed proportion details. These are available anywhere. The compressive strength was 70 MPa, and it was pumped for a distance of 120 meters without any problem. So workability was very good. This is a bridge constructed using your high performance concrete, Joigny Bridge in France. And then this is a Great Belt fixed link. This multi-element fixed link crossing, Great Belt straight between the Danish Islands and the New Zealand. It consists of a suspension bridge as well as the bridges. The total length is 6,790 meters, 31, and the longest span is 1,624 meters. There are 19 piers in water. This is what, so this we have the link connecting. And this is a pre-stressed ultra high performance concrete communication tower. They have the outer core and the upper steel and inner core, and then this is filled with high performance concrete confined, and the confined concrete like this, when you use, it gives you excellent performance. The communication towers you can use, and these are the properties of a mix that are being used for that pre-stressed tower. And then bridge in Tennessee. This is another bridge. This deck and piers completely of high performance concrete. The other bridges, the cable stayed bridge at Normandy. Then this is 656 feet, 200 meters central span with ribbed slab is constructed, and the cantilevered viaducts and the arch bridges at Ransom. Project rivers near Denon Bay. All road applications. The pylons of the Chavan suspension bridge. These are some of the examples. The cable stayed bridge, so you have. And then this is a suspension bridge. This is arch bridge, wherein you have the heavy columns also provided. And the water tower palace building. Water Tower Place. The Water Tower Place building built in 70s, completed in 76. It has 86 stories in Chicago. They're 262 meter high. The slump use was 100 mm. Here 15% class F fly ash has been used. So this is the water tower building. The specialty of this building is that for the entire structure, the range of strength used is different. So up to this point, they use 60 MPa, and then to this point around 50 MPa. So as they move up, they used the lower strength because the number of stories above are less, and then the load is less. Because this is a beautiful application, Woolpark's offshore platform, oil exploration platform, and it's a 2 million cubic meter of high-performance concrete was laid in this, ranging the strength ranges from 45 MPa to 70 MPa, and this is a beautiful view of this oil exploration platform, Woolpark's, and this is top view and the below water view. These things are available. And then concrete for underwater tunnels and even the tunnels and offshore structures, underwater structures, because the performance is a major issue. The durability is a major issue. And this is Silence Glaciers Viaduct that is constructed using the strangulated deck webs. And then this is the details of that. For a cross section, they used 60 MPa, and for the deck slab, they used 50 MPa. The details are available. You can see this is a Scotia Plaza building in Canada. A beautiful view of that building. The details: 60 stories, 70 MPa concrete in Canada. And case studies. Of course, this was our own study, so it is not required since we are running out of time. So I will conclude here. If you have any questions, then answer your questions.
Thank you, sir. Thank you so much for briefly giving us the knowledge on the high performance concrete and its properties and all. Thank you, sir. Thank you so much. Now I request the participants, if you have any doubt, you can unmute yourself and ask questions to the sir. Or even you can send your questions in the chat box. Participants. Sir, there is a one question from Santosh Kumar. What should be the optimum size of aggregate for high performance concrete?
Well, there is no single size for all grades. It depends on what level of strength you are going in for. Say if you are going for 60 MPa, that you can go for 20 mm without any hesitation. And 100, you want a M100, for example. So 20 mm may not be useful. You have to go for 12 mm. More than 100 MPa, for example. In that case, you have to restrict yourself to 12 mm or 10 mm downsize. That will be better, more than 100. So it depends on what is the range of strength that you are targeting for. So higher the strength, smaller should be the size. There is nothing like optimum.
Thank you, sir.
Okay.
Any other questions? Sir, there is one more question from Dr. Preeti A. Patel.
Yes.
Which type of superplasticizers are preferable?
Fourth generation are better. It depends on what is the water cement ratio that you are going in for. If you are going in for in the range of 0.3 or 0.32, then even SNF, SMF is okay. If you are targeting for say a water cement ratio of 0.2 or 0.25, so carboxylic based, that is a fourth generation, what generally called as carboxylic ethers and all that. So you have to go for that. It depends on what is the water cement ratio that you are starting with, and then what is your targeted workability. That also matters. But HRWRs are better than your SNF, SMF, and those things. Hello.
Thank you, sir. Thank you.
Okay.
Any other questions from participants? So thank you, sir. I think all the participants, there is no other question from the participants. Thank you, sir. Thank you so much for joining us and accepting our invitation and giving a talk on high performance concrete. As a token of love, we are presenting a this appreciation certificate, sir, on behalf of BLDA Engineering College and principal, head of the department, and the coordinator of this ATAL FDP, Asif Momin, sir. Thank you, sir. Thank you so much for joining us and giving this presentation. Thank you, sir.
Thank you. Thank you very much for your opportunity, as well as for the patient hearing from the participants who have tolerated me for 1.5 hours. Thank you. Thank you so much.
Thank you, sir. Thank you. Participants, the feedback for the this session will be sent through WhatsApp. You can give the feedback.